All right, so we started 2.5, implicit differentiation, last time. And when we talked about this, we looked at what was meant by implicit differentiation. In particular, implicit differentiation means that we have some function, or some equation rather, that maybe either can't be solved for y, or it's really complicated if we try. And so perhaps not doing things by solving for y is a better choice. And we had seen a couple of examples. This was one where we could have solved it for y. It was possible, but not solving it for y is actually quite easy. The process is very straightforward and very clean. The only difference that happens with implicit differentiation versus explicit differentiation is that anytime I take a derivative of something that has y in it, I'm going to get a dy dx. Okay? So that's the caveat. We had done two examples, I think. Is this our last one that we've done? Yeah. We've done two examples. This one was really messy. We did it in two different ways. This one was really clean. So just because it's implicit differentiation doesn't mean it's hard or it's easy. It really depends on the function itself, which is true for all the differentiation, right? You guys experienced that probably on the gateway, right? Some problems you use the product rule and they're easy, and some problems use the product rule and they're not easy. So it's not implicit differentiation that's making it difficult. It's the type of function that you're given. So we're going to do another example. We'll do several more examples. So this one we're going to find the derivative y prime of x, or dy dx, implicitly. And you'll notice that, again, we potentially could solve this for y. It would be possible. But we would end up getting a square root, and the square root's going to end up giving us a plus or a minus. And so that's going to make things complicated. And so we're going to look at taking this derivative implicitly. So on the left-hand side, we have an x squared y squared. And because they're multiplied, it means I have a product rule. So there are two pieces right here. Anytime I see two different pieces being multiplied with a variable in it, and now the variables are x and y, I have a product rule. So the product rule says I rewrite the first piece, and I take the derivative of the second piece. So the second derivative, or the derivative of the second piece, y squared, would be 2y. But then because I just took the derivative of something that contained y, I will have a dy dx. And then I need the product rule's opposite piece, right? Which is to take the derivative of the x squared, that's 2x. And I rewrite the y squared as such. And then we're going to continue. What's the derivative of 37? 0, so write it or don't. I'll write mine for right now. And then on the other side, what's the derivative of 4x? 4. Okay, so the majority of the calculus is all right there. Everything else, I shouldn't even say majority, all of it is. Everything else that we're about to do is not going to be calculus. Okay? It's going to be algebra. That's what it's going to be. It's going to be algebra. My goal is not to try to get y alone, like you sort of would do in an algebra problem typically, but it's to get the dy dx alone. And this one's nicer than the last one. If you remember, this one was really messy in some sense because at this point in the problem, we had several dy dx's. And we had to collect them all on the same side and so forth. This one's friendlier. I only have one dy dx. So I don't have to do a lot of the things I did in the last problem just because of that. So I'm going to move everything that doesn't have dy dx in it to the other side, which right now is just the 2xy squared. And I'm going to just kind of collapse this notation just a little bit. I'm going to move my 2 to the beginning, write this as x squared y. It is dy dx. And then my 2xy squared moved to the other side. Okay, is that step okay? All the pieces seem like where you see where you came from and so forth? Okay, good. Now, how do I get dy dx from here alone? I divide. So I'll divide by everything that dy dx is multiplied by. So 2x squared y So obviously these pieces on the left, the whole point in doing so is that they canceled out, right? All that cancels. On the right-hand side, we want to be a little bit careful about sort of over-canceling, right? Canceling things that you really don't cancel. My kids are working with simplifying algebra expressions right now in an Algebra 1 class, and it's not that much different. They try to make the same kind of mistakes that we all try to make when we look at this and say, hey, look, there's some x's and some y's, and let's just get rid of them, right? You can't just get rid of them. So every piece has to contain something for it to be eliminated. So on this one, because that 4 at the beginning is just a constant 4, what that means is that the only thing that they could all be divided by was potentially something that's divisible with the 4, right? That's the least complicated piece on the right-hand side. And so in particular, if you do look at all the pieces, and when I'm saying pieces, I mean the terms. So this is 1 term, 2 terms, 3 terms. There's 3 terms. We need a number or a letter or variable or whatever that is actually in all of them. And there is something. What's in all of them? A 2. They would all divide by 2. And that's it. There's nothing else that they will all divide by. So that is what we will do next. We will divide each one of them by 2. So if I divide 4 by 2, I get 2. And if I divide the 2xy squared by 2, I just get xy squared. And then if I divide the 2x squared y by 2, I just get x squared y. And because I don't have any way to simplify any further, that is, I don't have like a definition that says y equals somewhere, right? I can't do anything else. This is as good as it's going to get. All right, let's try another one. This one's got some trig in it. So on your gateway, many of you saw things that looked kind of like this, not with the x and the y multiplied inside of a trig function. I get that. But you wanted to sort of group them in different ways. The natural grouping, or maybe not natural, but the definitional grouping of what's actually going on here is that the x and the y are inside of sine together. Okay? If it was supposed to be like that sine of x was by itself and then it was multiplied by y, there would have to be parentheses put on here to begin with. And there were not. So the understood parentheses are actually right here. Is that okay with everybody? So sine is my outside function. xy is my inside function. And that xy on the inside is now a product. So we've got a chain rule and a product rule for the sine xy. Let's start with the derivative of the outside. What's the derivative of sine? Cosine. And it's cosine of whatever it was the sine of to begin with. We rewrite the inside. You do not take the derivative inside of an outside derivative. They're separate pieces. xy gets rewritten. After that, and I'll bracket it to sort of differentiate, there's an x times a y here, and I need the derivative of the product xy. So this is a product rule. Product rule says rewrite the first piece. Now I need the derivative of the y piece. What's the derivative of y? dy dx. You got it. And then I do the opposite. I take the derivative of the piece that's got x in it. What's the derivative of x?
1.
Just 1. And the y gets rewritten. That's the left-hand side. The right-hand side's easier. What's the derivative of x squared? 2x, and the derivative of the negative 3? Yeah, it's 0. So you can write or not write the 0, it doesn't matter. There's a couple of different things you could do in terms of solving this for dy dx. So let me just talk through the 2 options, and then you guys can tell me what you want to see me do, and we'll do it that way, because it doesn't really matter. So one option is that I could divide the cosine xy to the other side to start with. And then I'm just left with the part that's in brackets. Does everybody see what that option would sort of look like? Okay, that's one option. Option number 2 is that I can take the cosine xy and I can distribute it through the brackets. And that's another option. And both will give us the right answer if we proceed with all the algebra steps properly. What do you guys want to do? Do you want to distribute it or do you want to divide?
Probably divide.
Probably divide. Okay, let's divide then. I'm great with that. So if we divide, the only reason we can do this is because the cosine xy is multiplied by everything in that bracket. So this is cosine of xy on both sides. And this piece and this piece will cancel. I'm left with the part that's in the brackets, which is x dy dx plus y. And it equals now 2x over the cosine of xy. Okay, is this okay? Now, the benefit in the way that we just did it is it cleaned it up and looks really nice right now. There is there is a drawback. We're going to get to it in making the choice that we did. But this is a pretty good place for us to see this and look at this for. Now, I want to get the dy dx alone. What would I need to do next? Subtract the y. So the y is going to move next, okay? So we've got x dy dx equals 2x over cosine xy minus y. Then what would I do? I would divide by x. Does anybody see the price that we're going to have to pay? What happened? I have a fraction inside of a fraction, right? I've got this little fraction, 2x over cosine xy on top, and it's over another denominator, x. And I can't leave it that way. Now, it's not a big, hairy, horrible thing to have to deal with, but it is something we have to deal with. We cannot leave it like that, okay? So I'd like to propose on the right-hand side that instead of writing it as division by x, I write it as multiplication of something different. What is the same thing as dividing by x? Multiplying it by 1 over x. So I'm going to actually rewrite that step so you see it. Here. So I can actually distribute this through now. It does have to go to each piece. So the x itself will actually come into each of the individuals' denominators. The second one doesn't look like it has one. Of course, it's a 1. So this is like y over 1, right? So my next step, I need a little bit more space. My next step is that it's going to look like dy dx equals 2x over, I'm going to put the x at the beginning because I don't want to somehow inadvertently multiply it by the xy because xy is inside of cosine. The x that I'm distributing through is not. This is y over x. And what's going to happen in my first fraction? The x's are going to cancel. The x that's the beginning is going to cancel with the x on top. Nothing can cancel with the xy inside of cosine. That can't happen. But all of this on the bottom, because it's all multiplied together, is one term. That's different than happened over here, right? Over here, there's two pieces that are separated with subtraction in the numerator. They are separate terms. But anything that's multiplied is a singular term, and you can cancel things from it, but you can't cancel inside of cosine. So this x and this x will cancel, and I get dy dx equals x, not x, 2. 2 over cosine xy minus y over x. That's not the only way that this answer could be expressed. We canceled the x's here, and there's nothing wrong with doing that. But there might be reasons, not with this one, but there might be reasons at some point that instead of canceling an x, what you really wanted to do was combine the two fractions, right? There might be a purpose for doing that in a certain situation. So another version of this, let me just show you what another version of the answer could look like, is that instead of canceling what I had, is it minus? Yeah. We actually get a common denominator, which means I need a cosine xy over here, but the x is already there and in common, and I would end up getting 2x minus y cosine xy over x cosine xy. And this would be another equally correct version of a simplified answer. And one's not better than the other. They're both perfectly fine. And in fact, this version is what it would more likely look like if we had distributed instead of divided. Our answer would have naturally turned into this instead of it being sort of forced at the end just by saying, what if we get a common fraction? Or, one fraction, a single fraction. Okay, is everybody good with that? So I don't care if you do it that way. I'm just letting you know that is something that could happen, is that your version could look different than someone else's if you've done it differently. Okay, we're going to do the same thing, implicit differentiation on this, but we're actually going to evaluate it at the end. We've done this in a lot of situations from 2-2, 2-3, 2-4, where we do derivatives, and then we plug a number in. And in particular, you might be looking at this and saying, I'm actually going to have to probably, at least potentially, plug in both the x and the y, right? We haven't had to do that before. When they were solved for y, we only had to plug in the x value when they gave us this. So that will feel a little bit different. What properties do you notice that we're going to need to use on the left-hand side, x cosine y? Product rule, right? And then we've got the y inside of the cosine, so there's going to be that embedded chain rule going on because the dy dx is happening. So we've got a product rule though to start with. So we're going to write the first piece. Now I need the derivative of cosine of y. What's the derivative of cosine? Negative sign. I'm going to put the negative in front of the x. So this is negative sine y. Okay, the inside stays the same. But because I took a derivative of something that contained a y, I'm going to multiply this by dy dx. It's tempting to feel like you finished, but you didn't because it was a product rule. So there should be two pieces. Now I have plus. Now I'll take the derivative of x, which is 1. And I will rewrite the cosine of y. Equals what? 0. I can't tell you how many times people get to that point and they just write down a 1. You've done all the hard work and you just make that simple mistake at the end. So pay attention to those constants. They do have a derivative of 0. And as you look at this, you should notice, yeah, I've got x's and y's and dy dx's. There's 3 unknown quantities in this particular derivative, right? But it's okay. And in fact, you don't even have to simplify from here and solve for dy dx if you don't want to. You can actually evaluate it and then solve. So let me show you what I mean. We're trying to evaluate this with the 2 in for x and the pi thirds in for y. So I'm going to put them in. We're going to put the 2 in for x and the pi over 3 in for y. dy dx, I don't know. That's the goal. I'm trying to find that. Didn't really need the 1 anymore. Let's do cosine of the same y, pi over 3. Now the only thing I don't know is dy dx. I will be able to solve for this and simplify and so forth. Pi over 3 though, unit circle stuff, right? So on the unit circle, pi over 3 is approximately up here, right? I need to know the sine value and the cosine value because they happen to both be in my function. What are the sine and cosine values for that location? Okay, so one of them is root 3 over 2 and one of them is 1/2. Do you remember which one's which? Which one's x and which one's y? 1/2 is x. Square root 3 over 2 is y. This is the unit circle location we're talking about. Why does it matter? Well, or not necessarily why does it matter. Obviously, there's a reason it matters because one's cosine and one's sine. What I meant to say is, why do we know that it's that point and it's not flipped? Except for just basic, like we memorized it that way. Do you know how you can determine it if you forget? Which one's bigger, 1/2 or square root 3 over 2? Which of those numbers is bigger? Nope. Square root 3 over 2 is bigger. They have the same denominator, right? So the numerator is bigger with square root of 3 than it is with 1, because 1's the same thing as square root of 1. So this one's my bigger one, square root 3 over 2, correct? And if you can visualize what your unit circle looks like to know that you're up here, you should be able to decide which value is bigger right here. Is it the x value or is it the y value? That's y. Y is definitely a larger value at that location. So y is my square root 3 over 2. Okay, so how does that help us? Well, it helps us because cosine is x and sine is y. So now I can actually use those into my function. So the negative 2 is still here. The sine value is y. That's my square root 3 over 2. Got my dy dx here. And then the cosine value is the 1/2. All good? Okay, this one simplifies kind of nicely. I've got the 2's canceling. So I've got negative square root 3 only, and then dy dx. And then I'm going to move this piece, the 1/2, to the other side. Negative 1/2. And then what would I need to do to solve for dy dx? divide by negative square root of 3. And instead of actually writing it that way, I'm going to write it the way we talked about on the last problem. I'm going to write it as multiplying by the reciprocal, and it is negative, so the two negatives will cancel. This actually gives me 1 over 2 square root of 3. I will not leave it that way. What will I need to do? Yeah, it's a conjugate. It's a very simple conjugate, but you're right. We're going to take the square root of 3 and rationalize the top and the bottom. So square root of 3 times square root of 3 would actually give me a 3 times the 2 that's down there is a 6, and the top is square root of 3. And while it feels like you might want to reduce the 3 and the 6, you cannot. The 3 is under a radical, the 6 isn't. So square root 3 over 6 is the best we can do for this version. All right, let's go to the next one. Now we're going to actually find an equation of a tangent line. This one actually is a familiar object to you. Do you know what this is an equation for? I asked a question kind of like this last time, and it's not the same thing. This one is a circle. Yeah, it is. So it's a circle for two reasons. Number one, there's a plus sign between them. We had an example last time that had a minus between them. And then they're both squared, okay? And they both have a coefficient of 1, right? There's not a 1 here and a 2 here. I don't have that. So they both have the same coefficient at the beginning. This is a circle. It's a circle with a kind of funny radius, square root of 37, so a little bit more than 6 is my radius. So that's not a very friendly radius, but that is my radius that's involved here. We're going to take a derivative. Again, could we solve this for y? Yes. Would it be particularly nice? No. And it'll be actually really easy to do the derivative if it's left in this form. So what's the derivative of x plus 2 squared? You have two choices, and you know this from doing the gateway. You can multiply it all out, and then you can take the derivative. Or you can do the derivative with a chain rule. And the chain rule works really nicely here. So the 2 can come down. We rewrite the inside to 1 degree less, namely a power of 1. And we take the derivative of the inside of x plus 2. Well, the derivative of x plus 2 is just 1. And then I do the same thing for the y component. I take the 2 down. I rewrite the inside into a degree 1 less. And then I need the derivative of y minus 3. That is dy dx. Very good. And then I need the derivative of 37. 0. So in order to have an equation of a tangent line, I need 3 pieces. I need an ordered pair xy, which they give me, right? And I need an m, which I have to find. And m is the tangent, it's the derivative, which is the slope of the tangent line. So the slope of this tangent line, m, is actually found by the derivative evaluated at the point 44. So it's the dy dx. dy dx is going to be the m value I need when I put 4 in for x and y. And if you want, you can solve this for dy dx first, or you can do like we did in our last problem and evaluate it. And that's what I'm going to do. So I've got a 2 here. I'm going to put 4 in for x. I'm not going to write my power of 1 and times 1 because we know that that doesn't change anything. Another 2, and I'm going to put my 4 in for y. And I do still have to write the dy dx, of course, equals 0. So let's find some of this arithmetic. I have 4 plus 2, which is 6. 4 plus 2 is 6. And then 6 times the 2 on the outside is 12. Next one. I have 4 minus 3, which is 1, times the 2 on the outside, which would give me 2. And then I have dy dx. Now you'd be able to look at this and just tell me what dy dx is. But if it were more complicated and you couldn't, we would first move the 12 to the other side. So you'd have minus 12. And then we'd divide by 2. And we would get that the slope, which is what I'm looking for, or dy dx, is equal to negative 6. So that's my slope. My point is 4, 4. So I have y minus 4 equals 6, negative 6, sorry, times x minus 4. So I have y minus 4. I'll distribute my negative 6. It's negative 6x plus 24. Careful on your signs. Add my 4. And y equals negative 6x plus 28. Now, in terms of graphing this, we're going to graph it by hand. The calculator doesn't play very nicely with circles. You might remember that. In order to actually graph this in your calculator as a circle, you have to solve it for y, which was kind of what we were trying to avoid by using implicit differentiation to start with. I do have a grid, good. But we can draw this by hand pretty well. Only if I can line things up well, and I didn't. So what is the center of my circle? Do you remember how to do that? Okay, I'm going to take that as a no. Don't remember. Okay, center of the circle comes from these points with the opposite signs. So the center would be negative 2, 3. Okay, so over here, negative 2, 3. This is the center of my circle. The radius would be the square root of 37, which is a little more than 6. Okay, it's a little bit bigger than 6. So I can go out 6 in all 4 directions, like vertically and horizontally from where I am. And it'll be slightly more than 6. So there I am over here. A little more over here. A little bit bigger up here. And a little bit smaller down here. So those are going to be the locations of 4 of the points on my circle. We're going to see how well we can draw it. After I shift it, it won't be too bad. So this is, roughly speaking, my circle. It's not perfect, but it's not bad. So pretend it's a little bit better than it is. The point 4, 4 would be about right here. Again, it's not perfect, but it'd be about right there. And the tangent line that we just found is going to be something like, that's not bad, like that. And we can confirm at least a couple of things. It is a very steep negative slope, negative 6, and it would have a very large y value intercept, 28. So those things seem reasonable from knowing the basic graph of what this circle should look like. All right, I have one more example with dy dx, and then I have an application problem that actually comes from a little bit earlier in your book. So this one, do you know what this one's an equation for? I promise I'm not going to ask you what these are equations for on tests. I'm just curious if you know. Do you know what this one is? It's not a parabola. That's close. We talked about it last time. It's a hyperbola. Yeah, it's a hyperbola. So if it were a parabola, it would only have one of those squared. And it's got both of them squared. That's why it's not a parabola. And then if it were either a circle or an ellipse, we would have an addition between the squareds, and we have subtraction. So this is a hyperbola. So we're going to find, and notice the directions, they look a little funny. It says d2y dx2. This is notation for a second derivative. This is red. The derivative, I'm sorry, let me take a step back. This is red. The second derivative of y with respect to x twice. That's how you read d2y dx2. The 2's are in different locations, and that is purposeful. The second derivative of y with respect to x twice. Okay, that aside, what's the derivative of 2x? I didn't say that right. What's the derivative of x squared? It's 2x. All right, let's try again. How about what's the derivative of y squared? 2y, and then what? dy dx. And the derivative of 36? 0. Okay, at this point, I do need to solve it for dy dx in order to take the next step that we haven't seen done yet. So I will solve it for dy dx. So this will shift, I'll shift my 2y dy dx to the right. And we divide by the 2y. So the 2's cancel, the y's cancel, the 2's here cancel. So dy dx is x over y. Okay, good with that so far. Now I'm going to take the derivative again. So when I take the derivative of dy dx, I get d2y dx squared. Okay? X over y. What rule am I going to need? Quotient rule, at least if I leave it written like this, and I might as well. So this is low d high. What's the derivative of x? 1. Minus high, d low. What's the derivative of y? dy dx. All over low, y squared. Do you see how our second derivative has that first derivative, dy dx, still inside of it? But we know what dy dx is. What's dy dx? X over y. So we take this quantity and we put it inside of where I have the dy dx. So this will be rewritten. The y is just y times 1, so that's y, minus x, but the dy dx is x over y. It's not always x over y, but it is for this problem. We need to clean that up because I got fractions inside of fractions, which we talked about earlier as being a not okay place to stop. So right now this is y minus x squared over y squared. So far, so good? How do I get rid of that? Well, I get rid of it by multiplying by the denominator, y. But it has to multiply by both pieces of the numerator, not just one of them. So this gives me y squared minus x squared over y cubed. Now, in general, you may have to stop there. There is one more thing we can do on this particular problem. Do you see anywhere on our screen where we have a better way of writing y squared minus x squared?
36.
Very close to 36. Negative 36. Why negative? Well, let's first, where did you get the 36, David?
The very beginning equation.
Okay, so the very beginning equation has almost the right thing on the left-hand side. And Andrew, why is it not exactly right?
Because it's flipped.
It's flipped, right? It's reverse order. If I were to change all my signs, I would actually have negative x squared plus y squared, which is the same thing as y squared minus x squared. And that would equal then negative 36. So this numerator here is actually the same as negative 36 over y, and then it's over y cubed. That's unusual. That is not what you're going to normally see. Okay, are you ready to see a physical application that's easier to work with than implicit differentiation yields for us? Sure. Yeah, sounds good, right? Okay. So this is directly applicable to real-life settings like physics. So now that we can find derivatives, and I mean derivatives before implicit differentiation is where we're going to go back to for a second. It's easy to apply them to real-world settings like physics. So if we have a position function, position means your location in time and space, s of t, and we take its derivative, what we're actually finding is its velocity. Velocity is kind of like speed. It's like speed with direction. And then if we take the derivative of velocity, we get acceleration. So you can sort of liken this to driving your car. You've got a position where the car is at any given time. And if you're in the middle of driving, you've got a speed, right, a velocity that you're currently driving at. And if you're accelerating or decelerating, that's acceleration. It's how your speed's changing. So the application piece is really just about how we can use these pieces to find other information. Okay, ready for an example? So some of your examples are going to have far more, descriptive features with them in terms of application. I wanted to do something that's just pretty straightforward. So we have a position function, and the position function is in feet, and it asks us to find velocity. So velocity is the same thing as asking us to find the derivative. So we're going to find first, it's velocity, v of t. It's the derivative of position. And t's are being used here because t is for the time, right? It's a number of time, and it's time in seconds in this case. So we're going to take the derivative of negative 2/3 t cubed. What's the derivative of negative 2/3 t cubed? Well, you bring your 3 down. The 3 would cancel with the 3 that's in the denominator. So I'd end up with just negative 2 t squared. The second piece, negative 1/2 t squared. So again, the 2 will come down. It'll cancel with the 1/2. So that'll actually leave us with just negative t. The derivative of negative 3t is negative 3. And then the derivative of 27 is 0. Now the units that we get when we do this is feet per second, right? It's a rate. Feet was my original one, time is in seconds. So it's feet per second. If I'm asked to find the velocity, then after 3 seconds, what am I really being asked to do with this now? Yeah, put in 3 for t, right? Yeah. So I want to evaluate this at 3. So I've got negative 2 times 3 squared minus 3 minus 3. And if we evaluate this correctly, I believe we're going to get negative 24 feet per second. That's a speed, 24, but it's got a direction. It's moving in the negative direction. So in terms of a graph, it means the graph is actually going downhill, which we will talk about more in chapter 3. Speed, however, take a look over here. Speed's just the absolute value of velocity. So if I want the speed, all I need to do is to take the absolute value of what I found for v of 3. What was v of 3? Negative 24. Absolute value of negative 24 is positive 24. So speed's a very direct thing to find if we've already found velocity. And then the last one, acceleration, is found by taking the derivative of velocity, which happens to be the second derivative of position. You don't need to necessarily write all of those down, but I'm just wanting you to recognize that's what we're doing. So if we go back up to the velocity equation and we take the derivative, so I'm coming back up to here to take a derivative. What's the derivative of negative 2t squared? Negative 4t. What's the derivative of negative t? Minus 1. And the derivative of negative 3? 0. So it's just negative 4t minus 1. And if I want to evaluate this at 3, I will put the 3 in for my t. Left off my negative. Let me get that in there. Minus 1. So negative 4 times 3 minus 1 is negative 13. And I didn't write the units down a minute ago, but this is feet per second squared. Because it's feet per second per second. It's how my speed's changing. Right? It's the speeding up or the slowing down that happens if you were driving a car, for example.